Okay, so here we're going to carry forward looking more at the question of does it make sense to think of work as a change in energy? Let's consider one special case. So the equation we had from last time, which was in the case of a single particle that T1 plus U12 is equal to T2, this seems to perhaps result in some kind of a paradox. Let's look at a special case of it. Okay, special case where we are dealing with Coulomb friction. So let's suppose we have a block sliding over some surface, some slightly rough surface. Okay, so in the time interval from time 1 to time 2, this block advances. Okay, so this block is moving forwards. At some time in the future, it will be here. Let's consider this special case where we have no change in speed because it's still moving to the right. It's also no change in velocity. So as this block moves some distance s, it maintains velocity v. And we can suppose that some force P is compelling it to move. Now you might say, well, does it need a force? Because don't we know by Newton's first law that an object in motion tends to stay in motion? That's true, but we already have a force, right? We have friction. So there's actually some other force that is retrograde, which is our friction force. Okay, so force of friction, which we also have right here. I won't crowd the drawing. Let's make a free body diagram. Okay, so here's our free body diagram. Here's our particle. And again, we ask the question, what do the forces on me? Well, it would see a gravitational pull, which we call its weight. It would potentially see a normal force coming off the ground. There is this force P that's propelling it forward. And there is a force backwards created by friction. Okay, great. Now, we know that in the Coulomb force model, this is equal to, since this is sliding, mu k times a normal force, right? We've done this before. So let's go ahead and return to our expression T1, T2. What are those? Well, if we haven't changed velocity and we haven't changed mass, then before we've got 1/2 m v squared. That was my initial velocity. And we'll have the same term here. What about the work done? Well, I look at all of the forces that acted in the direction of the displacement. So because there was no vertical displacement, neither N nor W do any work. The force P is exactly directed along the direction of displacement. The amount of work it would do then would be P times S, that degree of displacement. Meanwhile, because the friction force is negative, that integral would have yielded a negative mu k n, that was the magnitude of the force, and S for the distance. So these two forces do work. This is exactly how much work they do. And on the right-hand side, T2, so we have 1/2 m v squared. Again, we've said suppose that the velocity doesn't change. Now you can imagine that this is very realistic. There certainly would be some amount of force you would have to apply to keep it moving, and if you were careful, you could keep it moving at a constant speed. So in other words, if this is equal to this, right, then this must cancel this. So we have here 0 equals 0. We can cancel whichever terms we want, but let's write it this way. 1/2 mv squared equals 1/2 mb squared. Now I'm writing it this way because what this suggests to you, it should anyway, is that there was no net work, because this is a special case of what we have up here, T1, T2. So if we have T1, T2, if this work term is 0, it means, apparently, that there was no net work. All right? And we could even say also, no change in energy. Now, I've kind of led you into this paradox on purpose, and I've been intentionally loose with the term energy, as I have been before, to try and remind you that we need to be careful. Because this idea that there was no change in energy should bother you. Why should it bother you? Well, what about energy in the form of heat generated by the friction? You can all intuit that as you're pushing this along, overcoming friction, some heat would be generated on the ground. Well, of course, the reason that we've run into this seeming paradox is because we have to be very careful about our terminology. And to try and tease apart this technical definition, let's start by building up slowly with some fundamental things. So first of all, let's talk about what is known as a conservative force. Okay, a conservative force is a force which does an amount of work in going from point 1 to point 2, or in going between points, that is independent of path. So let me just be clear about what that means. That means, for instance, that if you had chosen to move the block, okay, so let's consider two scenarios where you move the block from point 1 to point 2, and in the one case, you move exactly straight forward. Okay, so you just simply move the block here, and then maybe in another case, you sort of are going back and forth, and ultimately end up at 2. So there's this sort of zigzagging that gets you to point 2. You would all expect that the second path with the back and forth would probably generate more friction. You can imagine this an extreme case where you go back and forth many, many times before ultimately ending up at 2 and generating a lot of heat. So apparently, one of the forces involved here is not a conservative force. Why? Because the work that was done was not independent of path. That force times that distance added up to more down here. when we were moving to the right, the force was, in the case of P, the force was to the right, so we were doing positive work. When we switched around and we were moving back left, the force was in the negative direction. I'm assuming that rightward is positive. And the displacement was in the negative direction, so negative times negative, we're doing positive work. As we go right again, more positive work, left again, more positive work, so we'd add up to lots and lots of work, more work than we would get in the case of the first path. So P and the force of friction, by the same argument, both are forces that do not create the same amount of work independent of path. A corollary to this is that when a particle is acted upon by conservative forces, and conservative forces only, the particle is acted upon only by conservative forces, then the work done as a consequence of those conservative forces, the work done can be expressed as a change in potential energy. Now, I know I haven't defined potential energy yet. We'll do that in just a second. So, pausing on what exactly is potential energy, we can have another corollary then. If we return back to our initial expression for this lecture and we look at our expression for work and energy, the one that we had up at the top of the screen here, T1 is equal to U12 plus T2. Let's give that a name for this segment. Let's call this equation 1. So equation 1 can be reinterpreted as kinetic energy is a measure of the particle's capacity to do work. Okay? So, what do I mean by that? We've got this capacity to do work. We've got this hanging notion of potential energy. We need to resolve a couple more things exactly. What is potential energy? And when we talk about a capacity to do work, what does that mean exactly? And that's where we'll pick up in the next video segment.